In today's video, we will look at how to solve a VSEPR molecule problem. And we're going to start by doing a review lesson about what VSEPR molecules are and how to predict shapes of molecules. And then we will answer a sample question from one of the older AP chemistry exams from 2014. So we're going to start by doing a VSEPR review kind of lesson, and VSEPR, if you remember, stands for valence shell electron pair repulsion. And that's basically the theory that valence electrons like to repel each other. And because of the repulsion, characteristic molecule shapes will occur. So if I scroll down to this slide, I've tried to start off by summarizing the things that I wrote above. These are what I like to call our base VSEPR shapes. And so we have linear, trigonal, planar, and so on and so on. And what I mean by a base VSEPR shape is that there are no lone pairs on your central atom. So for example, if our central atom is A, and this is like an AX2, my linear, my actual molecule will look something like this. So linear is just going to go across. And there are no lone electrons on my central atom on A. So all of the bonds, they will repel each other equally. And for example, if these X's also have, let's say, these lone electrons on them, they're going to repel each other to the maximum distance they can and basically push each other away equally. So for example, the trigonal planar, if we were to do the same thing, we're going to put A in the middle. There's no lone pairs on A. And we're going to spread out the bonds equally and put our bonded atoms, our X atoms here. And again, the atoms are going to spread out equally because there's no influence. Nothing is on the central atom. There are no lone electrons contributing to a further repulsion. So the tetrahedral, trigonal, bipyramid, and octahedral, same thing. No matter how many atoms you have bonded, they will spread each other out equally. Now, from these base VSEPR shapes, if we remove an atom and replace it with a lone pair, we will get kind of a modification. So for example, if we take our trigonal planar, if we were to take off a bond, so if we look at our generic formula AX3, if we call it AX2E, where the E stands for a lone pair, lone electron pair on the central atom, then what this will result in is a bent molecule, because now I won't have space to draw all of them, but the reason why the shape changes is because that lone pair on the central atom, it will push these bonds away and creating this, so remember, I'm going to take off one of the X's, so it's going to push those bonds away, push them down. So not only do I have the effect of these atoms pushing each other away, but I also have the impact of the lone pair also contributing to its shape. So we do get a bent structure from our trigonal planar. If we modify our tetrahedral by taking away a bond, so let's say I call this now AX3E. Okay, so remember, I'm not going to label every single time, but remember the E stands for a lone pair on the central atom. This will turn into the shape trigonal, pyramidal. Okay, and then if I actually take away another atom from my tetrahedral and make another lone pair, so if I make this, for example, AX2E2, this will also result in a bent molecule. So that's another example of, it'll look actually very similar to the bent from our trigonal planar modification as well. Okay, so moving forward, if we take the trigonal bipyramid and we remove a bond, so if we turn this from an AX5 to an AX4E, so I'm going to have 4 bonds and 1 lone pair, this will turn into the VSEPR shape seesaw. Okay, it will help for you to have molecules or pictures beside you to help you review what these look like. And again, there's an influence of this lone pair will push away the bonds, and the bonds will push each other away, creating a molecule that's a seesaw shape. Okay, and an example of this very popular example is SF4. If we remove another bond, so if I take my trigonal bipyramid and I turn it into an AX3E2, so 2 lone pairs and 3 bonds, this will turn into a T-shaped molecule. And then if I take away another bond, this will turn into a linear molecule. Okay, so you may have seen a chart like this before. It's really helpful kind of summary chart of VSEPR. So now my AX2E3 has a central atom, 2 bonds, and 3 lone pairs. So we still have those 5 electron regions, and when everything repels each other, it will create this linear shape. Just actually be careful, this is linear asymmetrical, and there's another linear which we'll get from our octahedral. So let's actually modify our octahedral, AX6. So let's remove a bond and make it AX5, but we'll have a lone pair. And when we modify it this way, we'll get our square pyramid VSEPR shape. If we remove another bond, we will get AX4E2, and this will be our square planar. And then if we remove another one, this one, there's a lot of bonds, right? So there's a lot of modification. So if we go AX3E3, this will result in our another T-shaped molecule. And then if I remove one more bond, I'll get AX2E4. So still with those 6 electron regions, I'll get a linear here. But this linear, if you look at the kind of generic formula, you will get a symmetrical linear here, which this one is nonpolar. And then this one is asymmetrical. This one will be polar. There's definitely a lot to review for VSEPR. So this is a super quick summary lesson, just kind of reminding the names of the shapes and where they came from. But I do encourage you to look at diagrams online and in your notes to help you match the names of the shapes, as well as the bonding angles and polarity in more detail. But hopefully that helps for now. Okay, so with that kind of said, let's look at a sample problem from one of the older chemistry AP exams. This one's from 2014. And so there's more parts to this question. I just took a screenshot of this one part I wanted to focus on. So in the box, we're asked to draw the Lewis dot diagram for ClF3. And to help me do the answer, I've made a valence electron bank. So what I've done here is I've put how many valence electrons chlorine has and how many valence electron fluorine has, and I've added them up to give a total of 28 valence electrons. So when I'm drawing my Lewis dot diagram, what I need to do is empty my valence electron bank. Okay, so for example, I'm going to put chlorine, I'm going to put chlorine in the middle. Let's fix that here. And so chlorine will go in the middle, and the fluorines I'm going to surround the central atom. And when I empty my electron bank, what I'm going to first do is put bonding pairs first. So I'm going to put a bond here, and a bond here. And remember that a bond is 2 electrons each, so that's 6 electrons. So I've emptied 6, and now I have 22 valence electrons left. So now that I have 22 valence electrons, I'm going to put them as lone pairs around my fluorines first. Okay, that's what I have more of. So we're going to go 2, 4, 6. So 6 valence dots around each fluorine, because that will give it an octet, right? That stable 8 electrons. And if you count this up, I've used 6 electrons times 3 fluorines, so I've emptied 18 valence electrons from the bank. And if you do the math, I'm left with 4 valence electrons. So where do those 4 valence electrons go? They're going to have to go in the chlorine. There's nowhere else to put them. And that is how I do my Lewis dot diagram. And I can tell that, okay, so actually, sorry, let's do -4 here. So now my total valence electron bank is 0. Okay, so I've zeroed my electron bank. That's good. That's what we want to work on our Lewis dot diagrams to get them to work out properly. Okay, now if we look at the bottom question, it's asking me to classify the shape of ClF3 as a trigonal planar or a T-shaped, because that's 2 possible geometric shapes. And then it says that the student learns that the molecule has a dipole moment. So which shape is correct based on this information? So there's a couple ways we can do this. If we go back up to our summary lesson, AX3, if that would be trigonal planar. And so let me write it down here on the side. So if it was an AX3, this is a trigonal planar, and this would actually be nonpolar because it's symmetrical in 3-dimensional space. And all of these dipoles, they would basically have the same polarity, so they cancel each other out, right? There's no net dipole or no net charge. If we look at okay, so what I have in ClF3, I actually have AX3E2. So I know my answer is T-shaped. So I have AX3E2. This is going to be T-shaped. And this, if you can tell, right, because there's 3 bonds, that's the AX3. And the E2 represents 2 lone pairs on my central atom. So this one's polar. This is polar because, as you can tell, I have an asymmetrical electron distribution. Okay, now I know it looks a little bit symmetrical if you try to split it vertically, but if you look at it horizontally, I don't want to make this too messy, but if you kind of look at it from the top, like for example, from the top to the bottom, it is not exactly the same. And that's where my asymmetry comes in, as well as my asymmetrical electron distribution. So you can, I don't have a lot of space to write, but you can word that a little better for your justification and your, you can look at the AP answer key from 2014 as well to see kind of how they worded it. So this hopefully will help you tackle a VSEPR problem. Obviously, like I said, there's a lot more in VSEPR that I didn't go through everything because I wanted this to be a concise summary lesson, but I hope this helps you solve a problem like this for now. This is a very handy tool, my valence electron bank. And then understanding and studying a chart like this is also very helpful to remind yourself of the VSEPR shapes and the VSEPR names. But there's more details to look at here, such as bonding angles, polarity as well, and examples of more molecules that showcase these shapes. Okay, please leave any questions you have in the comments, and thank you very much for watching today's video. Take care.